we had a force number and we had the amount of time. And then they asked for the momentum. Traditionally, momentum would be mass times velocity, but the fact that we know momentum equals impulse. And the reason why is because they're actually opposite to each other. Momentum is movement, and impulse is trying to stop it and slow down that movement. Well, traditionally it would be m times v. I have an m, I don't have a v. The great thing is I do have an f and a t, and I know that j equals p. And because of that, I can go ahead and plug in the j, and I can say, well, j equals ft, which will still end up equaling p, the momentum. And they both have the same SI units. So for me, this mass is going to be extra stuff. And so all I need to do is multiply these two numbers. 10 multiplied by 0.10. 1 kilogram times meters per second. So double check your answers if you did it. Hopefully everything looks good. Next one. Says according to the Guinness Book of, can't say speak today, of World Records, the fastest recorded baseball pitch. Now wait a minute, I don't know how old this statement is. I don't know if there's anybody who's thrown a faster baseball, so just going to toss that out there. This is an old homework question. Somebody else may have thrown a faster one than Nolan Ryan. Just saying. Don't know yet, not me personally. It says in 1974, the pitch was clocked at 100.9 miles per hour. Oh, I'm sure people have beat that, right? I mean, I think so. Which comes out to 45 meters per second. Oh, wow. If this is 1 meter, can you imagine having 44, because it says 45, 44 more of these, and in 1 second a baseball can start from the beginning and get to the end in 1 second? That's pretty fast. That is pretty fast. So it says here, determine the impulse. Now, I'm going to go ahead and just determine the impulse, question mark J, require to give this baseball that has a mass of 0.145 kilograms, such a momentum. They also, I'm going to underline this one as a velocity. They're both velocity numbers, but we prefer meters per second. Now, if they gave it to us in centimeters per second, we can still do that. No worries. We would just use those units as centimeters per second. But they're asking for the J. I know, and you know, that J equals P. And remember, the P is the movement, the J is the stopping, okay? And so in this situation, I don't have, let's see, bless you, I have a V and an M, which would truly be the P, or the momentum variables. They would like to know the J. Not a worry, let's go ahead and solve for momentum, which is V times M, and we'll just call it the J, because J equals P. So for this situation, J equals mv, and that's A-OK. A-OK for that. The mass of 0.145, multiply it by 45 meters per second equals, hopefully you did this homework and you got something like 6.53 kilograms times meters per second. Not too bad. You're ready for the quiz to take. Quizzes, I don't think it's too hard. I think it's only 2 or 3 math problems. So I think you'll be good. NASA, it says here, has been experimenting with using airbags to soften the landing of crew exploration vehicles on land. What stopping time will be required in order, so what stopping time? I'm going to put a little question for T. What stopping time will be required in order to safely stop an object that has a mass of, here's my mass, 7,250 kilograms. Thank goodness it's in kilograms. I don't have to convert. Moving at a velocity of 7.65 velocity And they also gave us an average force in F. Okay. Well, personally, I definitely see a T, an F, a V, an M. My brain is going to go ahead and go to the momentum equals impulse situation over here. And I can have 3 variables and solve for 1. So I'm going to go ahead and write J equals P, or I can write for this situation FT equals MV. F, I have that 426, 0, 0, 0. Multiply it by the T. I do not know how much time that is. Let me scroll that up. Equals the mass of 7,250 kilograms. Multiply it by the velocity of 7.65. Hopefully you started using your algebraic skills. And when you did that, you were able to see that, okay, I'm going to have to get one side. I need to get T by itself. So for me, if I get divide by 426, 0, 0, 0, that can cancel out. Divide this side also by 426,000. So that way we can solve for T, and T is going to be in seconds. Definitely do the math. I actually multiplied these two numbers at the top earlier. When I did that, I had 55,462.5. Just so I can simplify it before I do the division. Go ahead and divide those two numbers. T comes out to 0.13 seconds. Double check my math, see how it is. Hopefully you got the same thing, or if I'm off, let me know. If not, let's keep going. We got some, hey, let's circle the right word that would make this statement correct. Well, we did the first one. Next one here, impulse is actually equal to, well, what's it equal to? Is it equal to force times time? Is it equal to momentum? Is it equal to inertia of an object? Some people, they turned in their homework, not everybody, but most did. And they circled force times time. Do we see that there might be another option? Do we think? Logan, what are you thinking? What did you circle? What did you put on your homework? Did you do force times time? Maybe. Okay. Chris, what did you put on your homework? Force times time? Because that is going to be the equation. But just thinking a little bit more. One thing that I think is cool about math, one thing that I think is cool about physics, unlike, biology, when it comes to biology, and let's just think about, for an example, DNA. C's are always with J. Like, there's no ifs, ands, or buts. If a C, a cyanine is not matched up with a guanine, we're going to have some major protein issues problems, right? Last thing we want is to be lactose intolerant because our genetic DNA didn't match up right or something like that. We produced the wrong protein. The cool thing with math and with physics I like is that there's more than one way to get around it. And I know that we talked about J equals P, or momentum equals impulse. Remember, momentum is the movement and impulse is stopping it. And didn't we just do some math problems over here for an example? We said J equals P, and so we called it J equals MV. Even though we were looking for the J, or impulse, we used the momentum equation. Oh, how about that? So the correct answer is force times time and momentum. Impulse is equal. Isn't impulse equal to momentum? We have it as an equation. Yeah, absolutely. This is one of those, let's think a little deeper And you know what, Miss Munson, you ain't gonna trick me. One thing I will say is that impulse and momentum are closely related, and it's in our notes, to inertia. So even if you circled all three, I would agree with you 100%. That would be a good argument. If you circled all three of them, I agree with you absolutely, because momentum is extremely closely related, and we wrote it in our notes, to inertia, right? It's closely related, and if momentum is related to inertia, then that means that impulse is related to inertia as well. But if anything, you should know that both of those answers are absolutely must be circled, not just F times T, okay? So don't let that throw you off. Let's keep going. It says here, objects that are moving with greater speed will be harder to stop. That's what the definition of momentum is. It says here, conservation of momentum does stay the same or conserved. The next one, momentum of a free-falling object will have greater momentum at the, oh, that's when we were talking about projectiles in the first semester, right? They're going to have greater momentum at the bottom of the path. Do you remember when an object was tossed up, its velocity went all the way up to what at the top? We call that non-zero acceleration, 0. Its velocity was 0, and if its velocity is 0 at the top of that parabola, then that means it has 0 as momentum. But as an object started to fall down, the vector of the object's direction is down, and gravity is also pointing down. What do we do when two vectors are in the same direction? We add them up, and that's the reason why when an object starts to fall, it starts to pick up speed, and so its momentum would be faster or greater at the bottom of the parabola. So that's something we talked about first semester. And then the last one, it says here, momentum of an object at rest is absolutely going to be 0, which is a valid number. Don't forget, we absolutely could have a negative number because we would talk about direction if that was a multiple choice question. A negative number would work as well. Now, since I have our homework out here, I'm just going to take a glance at homework number 4, just in case if you went ahead and just took a look at it a little bit early. If you didn't, no worries. But if you have it out in front of you, well, let's take a look at it, just in case. So if you were looking. Now, first thing is, I definitely understand and I definitely agree that momentum is a vector quantity. And a vector quantity means direction. Okay, one more time. A vector quantity does mean direction. And so, due to the conservation of momentum, the amount of momentum I have before the collision must equal the amount of momentum I have after the collision. I asked everybody, and I said it in our notes, hey, let's please do not worry about that negative vector or that negative when doing the math, because right now this is basic physics. Not everybody is going to be going into engineering. When you do take university physics and start taking your engineering classes, absolutely, you will take those vectors into account. So we're going to just ignore those, and we're going to know that that means a direction negative. So first thing is, the momentum of the bat is 80. The momentum of the ball is negative 40. Is it because it owes momentum, like you have negative $40 in your bank? No, it's not that you owe momentum. It's that the negative 40 is in the negative direction. So that means that the bat is moving to the right, the ball is just moving to the left. Now, that's what it's telling me. And I'm going to come over here and I'm going to just put a little line. And I'm going to say direction. Just so that way my brain knows that's what it is. But when I combine, because we did that in our notes, just in case for those of us who don't recall, and we have a quiz coming up and I want us to recall this info. Over here, we did this math of the ball that was moving before the collision versus the ball that was moving after the collision. And what did we do with the momentums of both balls? We added them and we found the net, which means add, before the collision. Then, after the collision, we found the net, which means the combined momentum after the collision. They actually came out to be the same number. Okay. So over here, when I get the number 80 and the number 40, I hope you get the number 120, right? Again, that negative is a direction. I'm asking you, please just ignore that. Please take that into account for those of us who are going to go into university physics. Now, if I have 120 kilograms times meters per second before a collision, then I should have 120 kilograms times meters per second after the collision. So for this, I'm going to go ahead and put 120 over here. Now, if the momentum of the ball after the collision is only 10, then the bat should be 110. Makes sense? Hopefully it makes a little sense. Because we have quiz number 1, I'm going to skip and go down to question number 3, which would help us for the quiz. Okay? It's going to get our brain thinking about quiz number 1. A marble is rolling at a velocity of, velocity of 1.5 meters per second with a momentum of p-value. What is the mass of this marble? Well, P equals m times v, or since they gave me the p-value of 0.10 kilograms times meters per second equals, I don't know the mass, but I can solve for that, and the velocity is 1.5. Now let's go ahead and isolate that m by itself by dividing by 1.5, cancel, divide by 1.5. The mass of the object should come out to kilograms, right? Just in case if anybody just didn't do it yet. Okay, homework number 4, that's what we're at right now, homework number 4. Now, just so that way we're still in the mindset of homework number 4, I'm going to take a glance at a little bit of question number 4. I'm not going to do it all, but I'm going to do a little bit. And if you did do it, then you can check to see if you got it right. Then we'll move on to our notes. We'll talk about the projects, take our quiz, and we're done for the day, okay, on a chilly Tuesday. It says here, number 4, in physics lab, there's this cart, this object, that has a mass of 0.5 kilograms moving rightward. Again, I know that momentums are a vector. So I'm going to come over here, and I'm going to say M1, because I do see that there's another cart. All right. It's moving with a speed of 100 centimeters per second. Velocity speed. Now, I will tell you that, well, that's the units they gave us. Some physics teachers, they're going to want you to 100%. You better convert that to meters per second. Well, you know what? To be honest, if you leave all of your numbers, because if you look at cart B, it's also centimeters per second. You can leave that as is, centimeters per second. When we do our lab for Thursday, we're going to calculate the velocity of a Nerf bullet coming out of a Nerf gun. You can leave it in centimeters per second. Read the lab. It might ask you to convert it to meters. It's up to you. Centimeters is A-okay, but that's what we would use for our units. It says here now, it's going to collide with cart B, which is heavier. So this is going to be M2, or object number 2. Which is moving. I definitely know that it's a vector, it's moving to the left, but I'm going to call this velocity 2 B, velocity 1 B. before the collision for object 1, before the collision for object 2. And remember, conservation of momentum. The amount of momentum before should equal the amount of momentum after. Hold up, in a closed system. If for some reason you do it and the math is off, well, is it because your computer, your calculator is broken? No, it must mean that you're in an open system, right? So just tossing that as a reminder. The two cars are gonna, stick together. They collide and get stuck together. I just want to toss that out there. Inelastic collision. Remember those words. Again, we have a quiz. We got elastic collision where they do not stick together. They bounce off. Inelastic, the word in means they stick into each other. And then explosion means that you start off with one object and it breaks into multiple pieces, right? Just trying to get your brain going back again. Next one, letter A. It says here, determine the momentum for cart A before the collision. And B says, find the momentum of cart B before the collision. Well, the equation for momentum equals M times V, M times V. Or this would be 0.5, and I'm going to multiply, and I'm going to ignore the vector of 100. I'm going to call this 1.5. Again, I'm asking you to please just ignore that vector quantity. And when I do the math, I actually ended up with 0.5 kilograms times centimeters per second, because that was the unit of its velocity. And then over here, I got 0.30, double check my math, kilograms times centimeters per second. Okay, so hopefully that's what you got. Double check it. I was ignoring the vector quantities, which is just direction. Yes, sir.
0.5 is a half, right?
Yeah.
Half of 100 is 50, not 0.5.
Oh, am my math wrong?
I think so, yes.
Anybody else? My math is wrong? Yeah, it should just be 50? What about the other one? Should it just be 30? Okay, no worries. Double check my math. Boom. Whiteout. Love that stuff. Whiteout was discovered by a secretary, I think in World War II era. Isn't that cool? That's cool. I love it. All right, so here we go. Math is doing better now. Draw a vector diagram. Ooh, I like that question. Of the momentums of car A and B before the collision, meaning that no one's touched no one. And when they do touch, I can see up here that they are going to stick together, okay? It says be sure to pay attention to each cart's direction and magnitude. Alrighty, so for me, I got A and I got B. And it told me that A was moving to the right, so I'm going to come over here, move into the right. Its vector is going to be 100 centimeters per second. Object B, vector arrow, is going to be, look at this, smaller than A. Why is that? We talked about that first semester. 20 centimeters per second. Remember, the size or magnitude of the arrow corresponds with the value. And if I have a bigger value, I should have a bigger arrow. If I have a smaller value, I should have a smaller arrow. Remember, we got to pull that stuff that we talked about last semester. All righty, especially for those of us going into engineering. Next question here. Determine the net momentum of A and B before the collision. Well, to do that, when you see the word net momentum, your brain needs to think add, and we can do that. 50 plus 30 equals 80 kilograms times centimeters per second. That's before. Well, what should it be after? Because the next question says, well, what about after? We don't need to do anything. We know that the after should always equal the same as before. 80. Okay, so I'm going to stop right there. I'm going to leave question number 2 and the letter F for you to do on this homework and practice on your own. That will be information for quiz number 2, and I don't want to stress your brain out for quiz number 2 info, if that makes sense. I just want you to think about quiz number 1. So I did a lot of that homework with you, and you should be ready to go. Okay, now I'm moving this out of the way. Boom. Out of the way, done. And I want to come to the notes. Like I said, we've got a lot of little things to do today, a lot of moving parts, okay? And so we need to get through our moving parts so then we can get to our projects, which are probably the part that you're interested in. And I'm going to allow to leave this blank for you to do on your own, okay? So remember, when you don't do the practice problems that I leave on the notes, when you turn the notes in on D2L, that's going to be -1 point for everything that you just leave blank. Look at this one right here. That one is blank. You need to answer it, right? I'm going to turn the page. Page number 2. It looks pretty done, except for you need to answer that question or you're going to lose a point. Page number 3, here's another question. If I set you up, you should be able to plug them in. Let's turn the page again. Page number 4 looks good. Page number 5 looks good. Page number 6 looks good. And again, if you were absent, it's not a problem. Just go to D2L and fill in the blanks or watch the video. But here, everything above is going to be fair game for quiz 1, but I left some blanks. So let's go ahead and get to those blanks right here. Okay, that way we can knock this out and I can feel so much more happier. It says talking about collisions. Now we did talk about collisions. True story, there's actually 4 types of collisions. But when it comes to basic beginner's physics class, I just think going over 3 of them is good enough. Okay, there's the 4th one called perfect inelastic collision. You can learn about that in university physics when you take it, if that's what you are going to do. But talking about collisions, it says over here, elastic collision is whenever objects, we talked about this already, are going to rebound with the same speed. Meaning that when they hit each other and they do not stick, when they bounce off, they're still going to bounce off. If they originally were moving before the collision fast, they're going to bounce off fast. If they are moving slow, then they're going to bounce off of each other slow. Okay? They're going to rebound with the same speed. It says over here, the total amount of momentum and kinetic energy is conserved. The objects do not stick together. The objects are not deformed. Oh, what do you mean about that, Ms. Munson? Deformed. Okay, let me give you an example. You got a baseball. You got a baseball bat. 99% of the time when you hit the baseball bat, it comes off of the bat and it's still the same shaped round ball. You got tennis and you got a tennis racket. And when you hit that ball with a tennis racket, the tennis ball bounces off of the racket and it's still the same shape. It didn't deform. It didn't get all crushed in or smushed. Does that make sense? That's what they're trying to say. There wasn't much deformation that was occurring. If it did, it was so tight and minute. But when deformation occurs, then now we're going to change a little bit of stuff. But when deformation does not occur, we consider that to be an elastic collision. The amount of speed they are going before they hit is going to be about the bounce-off speed the same. Okay? Inelastic collision. Okay, we talked about that already. Inelastic collisions, they do stick together. They do stick together. Okay? The next thing we need to know about that is that the total kinetic energy actually decreases. Or we say it's not conserved. We, quote unquote, lose some. Now, we know it's not loss, it's just energy transformation occurred. The next thing we want to say is that even though this happens, momentum is still conserved. And the next thing we want to talk about this topic is that when it comes to the types of collision, believe it or not, this is considered to be the most common type of collision. Okay? Elastic versus inelastic. And to top that off, when the total amount of kinetic energy decreases, meaning not conserved, I'm going to put a little comma over here. May or may not deform. May or may not deform. So from that little paragraph right there, I thought it would be nice to put it into a chart form. You know me, I like to try to simplify. I like to have little charts or little Venn diagrams or, flow charts for us. Here's a little chart that summarizes this paragraph up here. When it comes to momentum, I don't care if it's elastic or inelastic, it is conserved. But the kinetic energy, meaning before the collision speed versus after the collision speed. Before the collision speed, the elastic type of collision is conserved. Meaning, if they were moving fast before the collision, after the collision, those two objects bounce off and still move fast. But when it comes to inelastic collision, it is not conserved. Meaning after they get into this collision, when they get, quote unquote, stuck to each other, the velocity decreases and slows down. But stop and think for a minute. If I got two objects and two masses, and my masses combined into one mass, it's probably going to move a little slower now. And that's what this is saying, okay? Deformation. No, that tennis ball is still the same shape. That golf ball that got hit by the golf club or the soccer ball still maintains its shape. But on inelastic collision, no/yes. It may or may not deform. There might be some crushing. Do you remember when we talked about those crumple zones? There you go. There you go. And then stick together. They do not stick together. Yes, they do. Okay? Again, though, we were specifically just talking about elastic and inelastic, nothing yet when it comes to explosion. Explosion's a little different. It literally starts off at one piece and breaks up into multiple pieces. All right, so I feel a little bit better now that our notes are done here. I'm going to turn the page. Okay, over here on this page. I'm going to try to shortcut for us, okay? So we can fill this in and we can really get things rolling and be about done. M1 is going to be the mass of object number 1. All righty? And I'm going to scroll down and I'm going to say M2 is going to be the mass of object number 2. But don't forget, we can have an M3 and M4. We can have however many objects are going to collide. The next one after that, V1B is going to be the velocity of object number 1 before the collision. Just like V2B is going to be the velocity of the object number 2 before the collision. And then the A's, which we saw this when we were doing the math, is going to be the velocity of object number 1 versus the velocity of object number 2 after the collision. Again, if they stick together or don't stick or break apart, that just determines the type of collision. And we will maintain, or we will use that one original equation for all types of collision. We need to know how to manipulate it when we read the math problem. Well, I'm going to stop there because I do not want to go over those math problems yet, because those will be over quiz number 2, not quiz 1. Okay? So I'm going to put up those notes now.